Let's continue with the next topic. So this should be the lecture from Peter Matveyev, but he is not available due to some reasons. So I will try to do this lecture about analytical methods based on the synchrotron sources, synchrotron radiation. So first of all, what is a synchrotron? Basically, it's an accelerator of the electrons. There are three main parts on at every synchrotron. Okay. So first of all, it is electron gun and linear accelerator to create the first bunch of the electrons. Then these electrons go to the booster ring, they accelerating for higher energies, and then after this booster, they goes to the main storage ring, where they, due to the accelerating, they reach the maximum energy, desired energy. And if you remember, when we spoke about the detection of beta radiation, there was this one of the effect that is called Bremsstrahlung, so it's stopping radiation. Yeah, so it is the same principle is used here when electrons changing their direction, they create electromagnetic wave. And so there is a set of the bending magnets, so magnets that change the trajectory of the electrons. And due to this change of the trajectory of the electrons, the X-ray radiation is created. And we use this radiation that is called synchrotron radiation to make different analysis. So you can see there are different stations. So these stations, they are located on the line where the electrons changing their trajectory. So there is a direction of the synchrotron radiation that is created. And at different stations, people use different equipment to perform different types of analysis. It can be X-ray diffraction, micro X-ray diffraction, it can be tomography, it can be it can be EXAFS analysis that we will talk about, and many other techniques, including even the Meissbauer spectroscopy using the synchrotron radiation. So there are a lot of different possibilities. So there is the storage ring separately shown. This is the main ring where electrons circulate, and this synchrotron radiation is created in bending magnets. And then this radiation, as far as it is not a certain energy of this radiation, it's like a white light. So there is a different wavelengths of the radiation. We need to select the specific wavelengths from all of these wavelengths of the spectrum. To do this, we use monochromators. It's not only one, because X-rays is difficult to monochromatize them, to choose the specific energy. So normally it's 2 or even more crystals that are used to separate or to select the specific wavelengths. Then there is focusing optics that allows to focus our X-ray beam on our sample. And then there is something happening with our sample. We either detect this light, these X-rays that go through the sample, or we detect the fluorescence of the X-rays from the sample. So there are different modes, different detectors that are used for analyzing our samples. So there are many synchrotrons actually today in the world. There are just few of them in Germany, in France. In France, in Germany, in Switzerland, in Russia, in Kurchatov Institute, in China, and there are plenty of other synchrotron sources. There is one that is currently under construction also in Russia. One of the, I think it will be the brightest one, synchrotron in Siberia, in Novosibirsk. So there will be more synchrotrons, and they're very powerful techniques. We will see some examples later. So if we are talking about the measuring the intensity of the X-rays that go through the sample, then there is a simple law of this absorption of any electromagnetic wave. You've seen this equations several times already when we spoke about the attenuation of the gamma quanta, or probably you know this law, Lambert-Boger-Lambert-Baer law from the spectrophotometry, just UV spectrometry. So it's the same law of attenuation of any electromagnetic waves. So it is simply the exponent with the attenuation coefficient and the thickness of our target. And depending on the element, this attenuation coefficient depends on the element itself, also on the energy of the X-rays that goes through the sample, and of course on the density of the material itself. But also, it is very convenient and very important that these spectra, this absorption spectra, they are selective to the element. Because, as you remember, there is a certain energy of bonding of the electron in the atom or in the molecule. So you can see this maximum of absorption of the X-ray at the energies that are equivalent to the energy of the electron bonding in the atom. So, and as far as different elements have different energies of electron bonding in atom, so you can choose the range of the X-ray energy that will be specific for your element. Of course, sometimes there are some intersections of energies. For example, zirconium has a very close absorption energy close to the actinides. So there can be some problems if there is a mixture of zirconium and uranium, for example. But in principle, you can divide this spectrum. So again, the principle that is underlined in XANES spectroscopy or X-ray absorption spectroscopy is photoelectric effect, and we already know about this effect. So due to the photoelectric effect, one of the electron laying either on the K shell or L shell or M shell is knocked out from the atom. Then there is a vacancy, and then the cascade of the electrons that goes from the upper shell to the lower shells. But again, we will see this dependence on the energy absorption of the X-ray depending on the energy of these electrons, either on K shell or L shell or higher shells. Today, in principle, we will talk mainly about the XAS analysis. It is X-ray absorption spectrometry, and there are two main ranges of this X-ray absorption spectrum. It is either XANES, so it is X-ray absorption near edge spectroscopy. So this is our edge of absorption, and XANES analysis has a very narrow range, something like 50 electron volts. And then there is extended structure of this spectrum, and by analyzing this structure, we can also get some information. So that is called extended X-ray absorption fine structure spectroscopy. So from the analyzing of this spectrum, we can get information about the surroundings of our central atom. And our central atom, I will go back, it is one of these elements, one of the elements, not only this, any element. You can use it even for light elements. We are looking on the very local structure of this specific element. What means the local structure? It is. Let's start our second day of the second week of the school. Interesting. It is strong. And the Russian experience in this field. Safety, energy development. Yeah, is it correct? Interesting. What is happening here? Почему оно началось опять? Да, почему оно началось? And so it's our translation in YouTube, but somehow it started, I don't know why. So I think we can close it. Okay. Okay, sorry. So let's go further. Again, the local structure, the local structure of our central atom. It is first of all the chemical state, that means the oxidation state of our atom. It is number of surrounding atoms. It is the chemical composition of these surrounding atoms, distances to these atoms, and the angles to these atoms. And as I mentioned previously, this X-ray absorption spectroscopy is element selective, and you can use this spectrometry for any kind of sample. It can be solid or liquid, and sometimes even for gases. There is again this division of the whole spectrum on two regions. So it is XANES and XAFS, and from XANES spectroscopy, actually we can get very few information in just oxidation state and some local geometry. That means just a coordination number of the atom. And from this extended structure, fine structure, we can analyze the bond distances, the number of atoms, and some disorder. That means that we can estimate the how unideal the structure of our solid sample, for example. And XAFS, you can see that it's just one of the representation. This fine structure, it is the result of the interference of these waves created by the electron knocking out, and this interference from the surrounding atoms. That's why there's like a wave structure of this spectrum. So again, back to definitions. You can see in articles different abbreviations like NEXAFs, and actually NEXAFs and XANES, it is almost the same. So it is near edge X-ray fine structure, and X-ray absorption also near edge structure. So actually it is the same, but from historical point of view, you can see this abbreviation as well. And also XAFs, so it's X-ray absorption fine structure and X-ray absorption spectrometry, also very often used as the same words or the same abbreviation. So it's actually the same meaning. So what are the advantages of the synchrotron light? Why it is so powerful? First of all, it is very bright light, so it's extremely high flux of the photons. That means that you can measure your samples very quickly. Really, it can take just few minutes to obtain the whole information about your sample. Also, it can be suitable to investigate the reactions inside the sample. So if you have some chemical processes in your sample, you can see the this evolution of the process in situ by measuring the spectrum, because the intensity of photons is very high again. So it's enough intensity even in one pulse to be detected. So as far as it is very high intensity of photons, that means that you can investigate even very diluted samples. So it will be again enough difference in the intensity in the absorption of the X-ray to be analyzed. But also you can focus this beam down to even nanometers, so you can make micro XRD analysis or micro X-ray fluorescence analysis or even micro tomography of your sample. You can analyze just micron particles with very high resolution. And yeah, that is important for us. There is a good energy resolution, so we can choose the range of the energies that are specific to our element. Yeah, so to analyze only one element. And there are some examples again about what information we can get from by using this X-ray absorption spectroscopy. Again, as you've seen already several times, the migration of the radionuclides regulates by many processes. So there are many chemical processes, sorption, redox reaction, etc. And we can use this X-ray spectrometry to understand the chemical form or chemical speciation of the, for example, actinide or other element during the sorption. So why it is important? Because when we build the thermodynamic model for to predict the migration of the radionuclide, as you've seen today also from the lecture about this disposal and different codes that use the thermodynamic constant of the process. To write down the correct equation, you have to know what are the species inside your system. If you don't know what is the exact chemical form of your element in the system, you cannot write the equation and you cannot put this equation in the model. So it is important to understand what the exact species that are in the solution and also on the surface of the mineral particles or sorbents or bacteria or whatever. So only if you know the exact speciation, you can build the thermodynamic model. So there is an example of sorption of cerium free onto different minerals. So here it is titanium dioxide, it is iron oxohydroxide, so it's in goethite, and there is a manganese dioxide. So in these cases, you can see the typical sorption behavior. So it is like S-shape dependence of the sorption on pH. But here you can see the huge changes with the time. So with the time, after 1 day and 28 days, you can see absolutely different behavior of the cerium in the system. So it was analysis, what is going in this system. And so here is the overall spectrum of the cerium on different materials. And this is this pre-H area. So from this region, you can see these numbers, and it is exactly this area that is very sensitive to the oxidation state. So this near edge X-ray absorption structure is very sensitive to the oxidation state. And you can see it is the cerium dioxide standard sample. It is cerium-free standard sample, and they have absolutely different features. So here's oxidation state of cerium +3, and here's it is for cerium +4 from standard samples. And you can see that when we look on the system where cerium sort on either iron oxohydroxide or titanium dioxide, there is only features that are similar to cerium-free. There is no features similar to cerium-4. But in the case of cerium or cerium sorption on manganese dioxide, there is a clear feature of the cerium +4. So the cerium +3 in the presence of the manganese dioxide oxidized to the cerium +4, and the cerium +4, as far as it has higher charge, it has a higher sorption possibility or sorption efficiency onto mineral surface. So this is one of the example how we can understand what is going on in the system. And there is another system with plutonium. And with initial oxidation state, plutonium +5. So there's again a comparison of the sorption behavior of thorium tetravalent. You can see that the higher the charge of the cation, the more efficient sorption even at low pH values. So it's a very good sorption, very high efficiency of sorption. That is not the case for pentavalent neptunium, because pentavalent actinides, they are present in the form of these dioxo cations with the effective charge on the central atom not +5, yeah, but due to the compensation of the charge by these two oxygens, it is +2 and 2.2. So as far as it is very low charge, the absorption efficiency of the pentavalent actinide is very low. So they started to sorb only at near neutral pH and alkaline pH. But for plutonium-5, it is something in between. Yeah, so it's not like neptunium-5, but not like thorium-4. So what is going on for plutonium in this system? So two samples were taken after sorption for analysis by X-ray absorption spectroscopy. And you can clearly see that it is not only plutonium bonds with the oxygen on the surface of the particles, but also there is a clear identification of the plutonium-plutonium interactions. But what does it mean if you have the plutonium-plutonium interactions? That means that they located quite close to each other, and this is possible if you have plutonium dioxide particles in your system. So by analyzing the fine structure of this X-ray absorption spectra, it was revealed that there are actually two species of plutonium in the presence of the hematite. So it is one, the sorbed species of plutonium, and the second, it is the particles of the plutonium dioxide. So you can see here the standard distances for plutonium-plutonium interaction and plutonium-oxygen bonds in plutonium dioxide. They were taken just from literature. And you can see the same numbers for these systems. Yeah. So it is clear identification of these particles in this system. So it was confirmed also by transmission electron microscopy with high resolution. So when the plutonium at relatively high concentration, 10 to minus 6, was taken, it was observed not the even distribution of the plutonium on the surface of the hematite. So this is a hematite surface, but it was the formation of the crystalline-like particles. You can see from the electron diffraction that it is very good crystalline particles. And this crystal structure is the same as for pure plutonium dioxide. So it's not only the pure chemical adsorption of the plutonium on the surface of the hematite, but the formation of the plutonium dioxide. And it was also confirmed even for very low concentration of plutonium, even at 10 to minus 9 mole per liter concentration of plutonium during sorption. Maybe it's not very clear from this resolution, but you'll see this small poorly crystallized nanoparticles of the plutonium dioxide. So it was further investigated this plutonium sorption behavior on different materials, and it was shown that either if you have plutonium +3, +5, or even +6 in the beginning, if you have a surface, plutonium will be sorbed or attached, let's say, in the form of plutonium dioxide. It really likes to form plutonium dioxide particles in the presence of any surface. It can be hematite, it was titanium dioxide, iron oxide, so other materials. Another example is like a continuation of this work is the understanding the structure of the nanoparticles of the dioxide, either actinide dioxide or cerium dioxide, because you know that if you decrease the size of the particle, you have more impact of the surface atoms on the properties of your particles. And with the decreasing the size, you lose the information from the conventional X-ray diffraction pattern. So it is plutonium dioxide reference, so it's bulk plutonium dioxide. And you can see a very good resolution peaks in X-ray diffraction. But with very small size of the particles, we lose some information. We cannot resolve these peaks, for example, and it's not really clear if it is the same structure as plutonium dioxide or not. But with using the X-ray absorption spectroscopy, so it's one of the transformation of the spectrum, we can see that the very local structure of plutonium is the same as for plutonium dioxide reference. Again, independent on what was in the beginning. Either it was plutonium 3, 4, 5. The structure of these crystalline particles, nanocrystalline particle, is the same. It is plutonium dioxide. And another interesting example, it is structure of thorium dioxide. So thorium has only one valence state. It is only thorium +4. So there is no question, is it thorium +3 or not. It's only thorium +4. But even in this case, with the decrease of the size, we can clearly see the change of this feature in the spectrum of the X-ray absorption of the thorium. So we can distinguish between different positions of the thorium. Either it is surface atoms of thorium, or it is bulk or core atoms of the thorium. So, and their combination makes this thorium dioxide spectrum. So if you have a very big impact already of the surface atoms, yeah, you can see that you really have a change in the spectrum. And it was this technique was used to analyze the chemical properties or chemical state of cerium or in cerium dioxide nanoparticles, because it was a lot of discussion. Is the cerium on the surface of the cerium dioxide is cerium +4 or it is cerium +3? Because there is a lack of oxygen atoms on the surface, yeah, so there is non-saturated bonds of the cerium. And is it cerium +3 or cerium +4? And it was shown that even for very small particles, like 2 nanometers, so it's already a few dozens of atoms in the particle, there is a clear identification of the cerium +4 as a main chemical state in cerium dioxide. So it is with more resolution. And so there is a feature that, first of all, it is only cerium +4 in all nanoparticles. And there are this hydroxyl group on the surface of the nanoparticles that are responsible for some spectral changes. But again, it was a very good final point in the discussion that there is only cerium +4 in these nanoparticles. But it is not the case when we investigate the dissolution of cerium dioxide particles at different pH. So you can see that, so it's already the result of the analysis of all the spectrum, the dissolution of cerium, it is not only the pure chemical dissolution. Then you have a solid phase of cerium, hydrated cerium dioxide that goes to the aqueous solution. But it is clear results that the cerium +4 at acidic pH range, the dissolution takes into account also the reduction of the cerium from +4 to +3. And you can see it either from the modeling of the cerium solubility. So from the thermodynamic constant, from the thermodynamic modeling, cerium +4 dissolution curve should look like this. But in experiments, it looked like this. And again, with the use of the X-ray absorption spectrometry, it was revealed that in this case, cerium in the solution is really cerium +3. But in solid phase, it's still cerium +4. Just a few more examples on what we can do. We can analyze even very highly active particles, like Chernobyl fuel particles. Of course, if you have this shielding of your station, if you have permission to work with the radioactive materials, but still you can get from this investigation, you can get a lot of information, not only the composition of the particles, but from the composition of these fuel particles, from their morphology. So it was done with scanning electron microscopy, with the information about the chemical composition and the oxidation state of uranium, you can guess the conditions of the formation of these fuel particles. What was the temperature when these particles was formed? What was the time duration for the formation of these particles? So from these scanning electron microscopy pictures, you can see that it is really a spent fuel because of this porous structure of the grains. And there are different particles that were found. It is either pure uranium dioxide particles, or it is a mixture of uranium and zirconium oxide particles. So different compositions of these, or even pure zirconium dioxide particles. And it was interesting to understand what is the chemical state of the uranium inside these particles, and it was revealed that actually it is only uranium-4 in all these particles. So after all these years, so it was in 2015, this investigation, so it is almost 30 years after the Chernobyl accident, but these fuel particles, they're still in the form of uranium tetravalent with some non-stoichiometry, but still they are very stable, these fuel particles. So I showed you already this picture about the determination of these thermodynamic parameters in lab and verification it in real samples. And here is one of my examples that I like very much. It is how science can help to the real enterprises, to the real processes during the decommissioning, or let's say dealing with radioactive waste or radioactively contaminated areas. So it is an example from USA. It's Rocky Flats plant where the plutonium for a nuclear bomb was produced. And during the very long period of operation of this plant, you can see the huge territory that was contaminated with plutonium. So, of course, you should decontaminate or remediate this territory to be able to work or to use this territory again, or at least to leave the clean territory for future generations. So, according to the estimations of the Department of Energy of the USA that were made in 1995, to remediate all this territory will take something like 70 years, and it will cost 37 billion US dollars. So, very long time, very much cost, very high cost. But what was done by the company that take this contract for remediation of this territory, they investigate the chemical speciation of the plutonium with this X-ray absorption spectroscopy. And it was found that in these conditions, in this territory, plutonium is located only in plutonium +4 state. That means that it is mainly plutonium dioxide, and that means that it will be not useful, so it will be useless to use any chemical compounds, because plutonium dioxide is hardly soluble, so it will take billions of dollars to wash the soil, but with no effect. So, with this information, they used another technology for separation very fine grains of the soils, just to remove the smallest particles in the soil. And they did it in 10 years. not in 70 years. And it costs not $37 billion, but only $7 billion. So this information about the chemical speciation, the chemical state of the element in your soil can really help to save time and money. And it was good for company because they received this difference. 30% of this difference they got as extra money for them. So it's quite good for company. Yeah, and this is how the science and analysis can help you. And also this example I already showed you, but I would again stress a bit attention to this information that we can get from the structural study of the extraction systems. And one of the studies that we can do, it is EXAFS study. And with the analysis of the speciation of uranium, in this case, it is uranium extraction by one of the extractant, we can compare the chemical state of uranium in a standard solution. So it's uranium plus 6 nitrate. And it is the uranium in the crystal, so this crystals of the complex that we obtained from this organic phase. And you can see that it is absolutely different. Only the main feature of uranium-6 is clearly seen, but the second feature is different. And from this analysis, it was revealed the structure of the complex, that uranium simultaneously present in the complex as uranium positively charged part, so uranium O2 and 1 nitrate, so it's uranium, the total charge plus 1. And the second species of the uranium, so it's counter ion in the form of anionic complex of uranium and nitrates. So uranium O2 and 3 minus 1. So in one complex, you can find uranium in both not oxidation, so the oxidation stated is the same, but in two different forms, in positively charged and negatively charged. Another example for the extraction studies, it is understanding of the influence of different solvents on the extraction and separation of americium and europium, but by this extractant, so it is bipyridine molecules with this triazine substituents. And it was interesting to see this behavior. So it is separation factor. So a separation factor is just the ratio of distribution ratio of americium and distribution ratio of europium. So it is how selective the extraction system towards one of the components. Here it's towards the americium. And you can see from this dependence that there is a clear dependence of this separation factor on the permittivity of the solvents. So it's different solvents. It is octanol, hexanol, cyclohexanone, and it is nitrobenzene. And the separation factor depends on the solvent. So many EXAFS analysis were done for the systems, and you can see that there is almost no difference in the spectra for different diluents. Yeah, they're very similar. Looks, I would say, the same, and it was really seen that the composition of the complexes, their structure, is independent on the solvent. So for americium, it is this kind of surrounding of the americium. So it's two ligands, these two organic ligands, and one nitrate in the inner sphere of the complex. So of course, in outer sphere, there are two more nitrate groups to compensate the charge. And for europium, it was only 2 organic molecules in the inner sphere and 3 nitrates in the outer shell. But still, what was the difference between the solvents? And the difference was in the distances between the cation, americium or europium, and the organic extractant molecule. So even if the composition, the structure of the complex is the same, but these distances, they're changing, so you can clearly see this change. So it's enough change to be seen to say that it is not uncertainty, but a real change in distances between the cation and the organic molecule. So from this investigation, what is good, why it is important? Because again, to get this information, you don't need to get a crystal, monocrystal. Normally, we can get information about the distances from central atom to the organic molecule. If we have a very good monocrystal of this complex, then we make a single crystal or monocrystal X-ray diffraction, and from this deconvolution, or let's say, or analyzing of this X-ray diffraction, we can get very exact position of the atoms, even hydrogen atoms. But again, to do this, you need to produce a very good monocrystal, and it is not always possible. But in this case, it is just analysis. And also, yeah, if you have a monocrystal, so solid phase, it doesn't mean that you have the same speciation in the liquid phase, yeah, because they're different aggregation state. So these techniques, this X-ray absorption spectrometry, can give us information directly from the liquid phase, and it is very good, very important. I told you that we can use the synchrotron light source to make all this analysis, but today more and more lab spectrometers are constructed. And at our division, we have also this lab spectrometer. It just like this table, half of this table, that allow us to make the same analysis as a very huge synchrotron source. Of course, as far as we use not a synchrotron source, but just a X-ray tube, the brightness of our source is much lower. But still, even if we have not so bright flux of photons, we just spend more time to get the same statistics as from synchrotron. So also there is after sampler for our samples, so we can make it in automatic mode to change the samples. So there are main parameters of our X-ray tube. So the range of the energies is quite limited, but is enough to analyze, I would say, half of the, maybe more than half of the periodic table. We can use it to analyze also actinides, and we did it already. We analyzed uranium, thorium, plutonium, neptunium samples. So it's a very convenient technique. It's just few examples of the spectra that we can get with this lab spectrometer. It is example of analyzing of manganese standard samples. So metal, trioxide, and manganese dioxide. And it is comparison of our lab spectrometer, spectrum for our lab spectrometer, and the Kurchatov beamline. So from the synchrotron source spectrometer. So you can see that the quality of spectrum may be, not so ideal, but it is very close to the real synchrotron source. So another example for uranium dioxide sample, also the comparison of the synchrotron source and our lab spectrometer. Again, there are more noisy, I would say, spectrum, but the quality is enough to get the information, structural information of the uranium. So normally, when you want to make the analysis on the synchrotron source, you have to make an application. So you fill up this application form, what will be the samples, on the composition, what information you would like to get with the analysis using this source. And then your application evaluates by the council, by the scientific advisors of the synchrotron facility. And after, let's say, a few months, you have a decision. Either your application is approved, and then you can go and make your analysis. Not also in the schedule of the work plan of the synchrotron source, or your application can be not approved, and then you will not get the results for your sample. So it's very long procedure to analyze your samples with the synchrotron source. In this case, lab spectrometers they are much more easy to be to have access to them, because lab spectrometers, so in our lab, it is not a huge facility. You don't have this very complex structure of the different people. You can just write email to the head of this facility, and most probably you will get some time to make this experiment. Also, it is very convenient that we have a lab and the spectrometer, let's say, in the same, at least, building. Yeah, you can make your sample and immediately analyze it. It is not always possible for synchrotron sources, because they normally don't have this chemical lab, or it located in some distance, especially if you are working with radioactive samples. For example, at ESRF facility in Grenoble in France, they have special line, this special station to work with radioactive samples, but they prepared in Germany. So it's Rosendorf beam line. So it is center Forschungszentrum Rosendorf, Research Center Rosendorf in Germany, and they prepared the samples there. Then they transported to France and then analyzed. So it takes a lot of time, a lot of efforts, and due to this transportation, your sample can be changed. But for lab spectrometers, of course, it is much more convenient. You can do immediate analysis of your sample, or from another point of view, you can perform long-term experiments. Just leave your samples in the lab again for some period of time, measure it again, and it is not such a problem, because for synchrotron facilities, you first of all you depend on the on the facility itself, on the quality of the electron beam in synchrotron. Sometimes it's stopped for some reasons, for some technical reasons, and engineers work hardly to start this this electron beam again. So sometimes you don't know how long it takes for them to start the facility again. For example, in Kurchatov Institute, some few weeks ago, the beam just stopped for 2 weeks at least, and of course all the experiments they shifted, so a lot of problems. There are no such problems with lab spectrometers, just X-ray tube. You just turn it on and there is a beam. But of course, it's all good for lab spectrometers, except one thing. It is not so bright as synchrotron source. And your measurements will take a much longer time. For example, to measure these standard samples that I showed you, this comparison between the spectrum in at synchrotron source, it will take, let's say, 5-10 minutes to measure your sample, and with live spectrometers it takes 1 day. So the time is longer with lab spectrometers, but it is more convenient. So from this point of view, you can really use these lab spectrometers to pre-characterization of your samples to see if your sample good enough or has some interesting peculiarities in the structure or oxidation state. And if yes, then you can go to the synchrotron source to make a more detailed analysis if you wish. So it really allows you to have the necessary time at synchrotron facility for maybe for more important samples, so you can choose your important samples. And also, we use it for education of the students, PhD students, and for training. So it's very good. So, in concluding remarks, I would mention that synchrotron-based methods. So first of all, they're non-destructive. You have your samples, and there is just a flux of X-ray, electromagnetic quanta, and you analyze your sample. These methods, they are element selective. So because the energy of electron bonding is depend on the chemical composition. There is no need to make a vacuum in the system. Sometimes we put helium back between the X-ray source and the sample, because, for example, if we analyze light atoms, where the energy of the X-ray is low, the lower the energy, the more it absorbed even by air. So we just need to remove air between the sample and the X-ray source and the detector. So to do this, we don't use vacuum. We just put back with the helium, and then we remove air simply by putting the back with helium. This method really have high resolutions, and if it is synchrotron based, it is high intensity, so it's very fast, and we can get a lot of electronic and structural information that are important to build our thermodynamic model and to understand, in principle, what is going on in our system. Also, we can use these techniques to analyze in situ reactions. And even with the lab spectrometer, it was interesting study of the batteries to analyze the oxidation state of I forgot, nickel or cobalt. I don't remember exactly what they did. So they take the batteries, they charge them and discharge, and make this spectral analysis of the cobalt or nickel inside the battery. So without, so it's non-destructive analysis to understand what is happening inside the battery during it charge and discharge. So this is also possible. So I think it is my last slide. Yeah, thank you for your attention. If you have any questions. If not, you can ask me later. So let's have 10-15 minutes break, and we will start a bit earlier our next lecture. Okay?
Например. Опа.
Переключай.
Все. А на запись, что ли, идет? Зачем кому
Да.
микрофон? Я поняла. Все, да, нормально.
So, dear colleagues, we continue with the next lecture about the characterization of contaminated samples from the environment by different sophisticated technique. The presenter is Dr. Irina Vlasova. So, please.
Thank you very much, Vladimir. Hello, everybody. We will speak about characterization of contaminated environmental samples. And the contents of our lecture is, firstly, we will speak about why, what, and how do we characterize contaminated samples. Then we will try to classify all the methods to some classes, groups, and speak in details about autoradiography, advantages and limitations of these methods, about electron microscopy methods, Raman scattering spectroscopy, X-ray methods, brief listing, and some partially destructive methods like PIXI and mass spectroscopy analysis. So we will speak about advanced techniques for characterization of radioactively contaminated samples. What is the reason to speak about it? Our goal is to choose an approach to perform decommissioning, rehabilitation of some contaminated site. For this purpose, we are to have the complete information about the forms of radionuclides, about matrix composition, about the binding of radionuclides to this matrix, and the mobility of radionuclides. And this information, the best way to obtain such information is non-destructive methods of analysis. What kind of radioactively contaminated objects we will speak about? Firstly, there are a lot of historical nuclear legacy sites in some countries, in some nuclear countries like Russia, US, and Great Britain, and France, and some else. These sites have been organized at the time when nobody think about the ecology and the influence on human beings and so on. The main idea was to make the weapon-grade plutonium very, very fast. So there are a lot of radioactively waste temporary storages, like surface storages. This is Lake Karachay, which is closed now, but there are some other lakes like this one in Russia. Subsurficial storages like tanks in Hanford site. I think you know about it. Some of these tanks are not closed. There are some released to the environment of this waste. Nuclear test local places, nuclear testing of bombs, uranium graphite reactors, and some other radiochemical plants, and so on. Each of these objects is complex, heterogeneous object, and we have very many unknowns about what kind of radionuclides, in what forms, what is the matrix, and so on. And if we are to think about decommissioning and rehabilitation of this site, we are to know all these unknowns. So what is speciation of the main radionuclides? How is contamination distributed in a landscape scale, in a some meters scale, in centimeters, millimeters, and micrometers scale, in order to perform proper sampling at first for some destructive analysis, and then to rehabilitate this territory. So our task is to characterize radioactively contaminated samples And we've got a lot of different techniques to perform the analysis. What technique or combination of techniques could help us? Some of them are like this one, are based on the laboratory instruments. This is a transmission electron microscope laboratory. This is tomography X-ray. This is X-ray diffraction equipment. And another kind of methods are based on synchrotron light. It is not so simple to use it, but in some cases, we are to use just synchrotron light in order to research, to study the speciation of radionuclides. So the question is how to obtain the maximum information with the least cost and in the least time. So we are to choose the optimal set of methods. Now, no method, single method cannot answer to our questions. We are to use some set of methods of different physical principles, of different advantages, and we will try to classify these methods. The very simple classification of methods is according to the presentation of information. There are three big classes. The first is imaging and visualization methods. So some methods could be just imaging and spectroscopy and diffraction, but I mean the kind of presentation of information that we can obtain from them. So imaging and visualization, spectroscopy analysis, you know what does it mean, spectroscopy? It is distribution according to energy. And diffraction scattering, it is just not the same. It is another physical principles. So non-destructive methods of analysis are interesting for us because we can reveal forms of radionuclides without destruction. A gamma spectroscopy is the first method of characterization. We use gamma spectroscopy firstly for any unknown sample. But as I understand, you've got the talk about gamma spectroscopy. We will not speak about it. We will speak about local microanalysis, firstly autoradiography analysis, which could reveal heterogeneity in the distribution of activity, or homogeneity if it is so, and micro-Raman spectroscopy. It is like phase analysis based on laser light, scanning electron microscopy with energy dispersive X-ray spectroscopy, which can reveal morphology, elemental composition, and phase analysis based on electron beam, X-ray tomography, which could show us density distribution in 3D in the volume of the sample. It is based on X-ray beam, and some other X-ray methods like diffraction and fluorescence and X-ray absorption spectroscopy and some else. All of them are based on X-ray beam. And conditionally non-destructive, partially destructive methods, mass spectroscopy with secondary ions, could be used for such local analysis too. If we try to classify all the methods according to the excitation and recording of signal, we can build such a table in which you can see the excitation of signal using passive techniques without excitation, photons, beams like laser or gamma ray or X-ray, thermal neutrons. Here we are to use a reactor, nuclear reactor, electron beam like electron microscopy, and multiply charged ions in the case of mass spectroscopy and pixie analysis. So let's see, and we can classify the methods according to their recording of signal. We can obtain photons or electron protons, alpha particles, multiply charged ions as a result, as a useful signal of our method. So the first class of methods are passive techniques, and we will speak about them in details. It is different kind of radiography, which can obtain gamma or electrons or alpha particles or some spontaneous fission. Another class is induced methods, that signal in which is induced by X-rays or laser light or gamma rays. So in this class, we can find X-ray absorption methods, X-ray diffraction, micro-Raman and infrared, X-ray photoelectron spectroscopy, and mass spectroscopy with laser ablation. We can say that it is partially destructive methods, but the destruction is very small, some micrometers, and gamma radiography using fission. Based on thermal neutrons, it is the methods based on nuclear reactor. First of them is neutron activation analysis. It is not local microanalysis, it is a bulk analysis of the whole sample. And it could show the composition, elemental composition of your matrix and radionuclides. And here it is fission radiography induced by neutrons, thermal neutrons, and alpha radiography based on some nuclear reactions. And the next class of methods are excited by electron beam. Here it is electron microscopy of different kinds, Auger spectroscopy, and some else. And methods which is excited by multiply charged ions, proton or particle induced X-ray emission, and mass spectroscopy with secondary ions. I think that the idea is clear for you, just classification. And if you have some new for you method, you can place it here to this table. Let's begin from passive techniques. The most popular passive technique in radiography and in radiometric analysis is autoradiography, which does not use any excitation. It is only the collection of signal from the radioactivity contaminated sample. There are two classes of detectors. Detectors for autoradiography must be sensitive to radiation and must have special resolution. So it is not bulk method, it is local microanalysis method. There are two main kinds of detectors: storage detectors and detectors in real time. Many kinds of detectors come to us from medicine because it is the sphere of very fast development of different equipment, and we use them in our scientific researches. The first kind of detectors are photoplays, X-ray films, nuclear emulsions. You know that radioactivity phenomenon was discovered using photoplate. It was the first discovery of radioactivity. All of these detectors needs chemical pretreatment to reveal the signal. And here it is solid state nuclear detectors for charged particles. It needs chemical pretreatment too. The second kind of storage detectors is laser-induced luminescence detectors like imaging plates, autoradiography. And the detectors in real time, like semiconductor diodes, solid-state scintillators, is not so so useful for our researchers. It is very good used in biology and in medicine. They are just high cost and not so convenient for us. In our researches, we use autoradiography with imaging plates and solid-state nuclear detectors for charged particles, exactly for alpha particles. The advantage is that in this case, we have the signal only from alpha particles, no beta. In our contaminated samples, it is very important to reveal the contribution of alpha activity, because all alpha emitters are long-lived. The most part of alpha emitters are long-lived, but the dose today, the high dose is from beta emitters like cesium-137, strontium-90. So this big activity is not useful for us when we are to see only alpha emitters. And that's why we use two kinds of detectors. Here it is the total activity, gamma, beta, and alpha. And here we can see only alpha activity. Let's see what kind of process are in imaging plate autoradiography. They detects all kinds of radioactivity. We see here it is imaging plate. This is phosphor layer with phthalate bromine of barium doped with europium 2+. And after some radioactivity in close contact with this phosphor layer, we can see after exposure time, we can see after excitation light, photostimulated luminescence from this stored activity in this phosphor layer. And the very good thing is that these imaging plates are reusable. We can clean it, erase all the signal using visible light and use it for many times, about thousands and many thousands of times. So this is the physical principles paper, very good in details, show what kind of processes are in this phosphor layer. Imaging plate radiography contains of three main blocks: detector, reader, and digital electronics. And detector is a imaging plate with blue side, which is phosphor layer, black side, it is the just the support, plastic support of this phosphor layer. It contains of crystals of barium phthalate bromine. And during exposure, imaging plate is placed in close contact with the radiation source, and europium 2+ is ionized to europium 3+, and radiation energy is stored in bromine vacancies. The second block is reader. It is a special laser scanner for this imaging plate. During reading, laser source stimulate photoluminescence in sensitive layer. The unstable europium 3+ goes back to initial state by releasing photons, which are collected by photomultiplier tube. And after that, we can see the image on the monitor and can collect these images. Visualization of the obtained image, it is a conversion of the luminescence signal to a digital form by special digital electronics and software. Let's see some examples of the using of this imaging plates. For instance, here it is some samples from Semipalatin's test site, weapon explosions. They are collected in some bags, zip bags, and here it is agreed with the cesium 137 and ink to see this grid on the autoradiography. And you can see that the distribution of radioactivity is highly uneven, and we can show some, we can see some hotspots with high activity, and not only localized these radioactive particles, alpha, beta emitting nuclides, but we can make something like semi-quantitative analysis, because this software can measure digital luminescence in digital luminescence units, this photostimulated activity, which is proportional to the radioactivity of the sample. So we can compare radioactivity of different spots and choose the spots of interest to the further analysis. Do you have some announcement? No? The next example is of using of imaging plate radiography of legacy soil on the territory of the uranium hexafluoride conversion enterprise in Angarsk. You can see different kind of technogenic soils and just the same grade, and we can see what kind of fragments of soil has much radioactivity and measure it and take it for the further analysis, so we can optimize the sampling of our radioactivity contaminated samples. Another example is from some aerosol material from Chernobyl nuclear power plant, different Petranov filters of different effective diameter. And you can see that exposition time is 15 minutes on the first filter and around a day in the second and third filter. And you can see that the main activity is concentrated on the first filter of this aerosol material. And we can reveal the distribution among these aerosol particles. The very convenient part of this method, imaging plate radiography, is the possibility to control any action with the sample. You can cut the wipe and displace the parts, separate the particles, and you can see if this particle is just still in your sample, in your preparation, or it goes somewhere. This is the cutting, and you can separate two parts of the wipe with radioactive material and cut again, and just take one particle from big preparation. And just another example is from literature from here. It is very interesting because they use imaging plate radiography for big scale analysis, for some meters analysis. The problem with the radioactively contaminated sites is that some of the buildings are contaminated, and you cannot take all the building to the waste. It is not a good idea. So we are to localize the places that are contaminated. And they use about 1,000 autoradiography images to control the big wall and find the places of local hotspots. The problem was that this contamination, as I remember, it was technetium, cannot be revealed by dose radiometer. It is not gamma emitting nuclide, but beta emitting, and that is why they used such imaging plate radiography analysis. So the result was that they can reduce the volume of radioactive waste. So autoradiography, just to conclude about this method, has some great advantages. It could optimize sampling process. I would like to say that destructive methods of radioactivity analysis needs around 1 gram of material. And radiography could help us to choose the proper representative sample of this contaminated area. Imaging plate radiography could detect hardly determined BT emitters like tritium and radiocarbon and strontium, technetium, and so on. So this is the advantages of this radiography. And let's go to another method of autoradiography analysis, which we used in our laboratory, alpha track analysis, which could be used only for alpha emitting nuclides and higher energy charged particles. It used a special plastic alpha detector, polyallyl diglycol carbonate, and it needs etching of a detector before reading. A latent track has a diameter around some nanometers, and after etching, it is around tens of micrometers. So we can use optical microscopy to compare the sample, the preparation, and the alpha track detector to find the local spots of high radioactivity. I didn't talk about the limitations of imaging plate radiography. It is very sensitive. I spoke only about advantages, but limitation is that you cannot use any exposition time. It is very sensitive method. It could record any cosmic rays. So 1, 2, 3 days, and it is just gray, and you cannot see any useful signal. It is a problem. So if you have enough signal, it is good. But if it is very low, emitting nuclides, so it is a problem. But for alpha track analysis, it is not so, because you can use any exposition time, any exposition period, minutes, weeks, months. If you have a time, it could be years, due to no fading of hidden alpha tracks with time. So we can detect very low activity of alpha emitting nuclides. And each alpha particles to this plane could be detected. And I will say about the energy measurement. The fact is that each pit of the alpha particle has some characteristics, some parameters like length and so on, diameter. And you can see that due to different energy, the shape and the length of this track differ. And we can perform something like alpha energy definition if we use some reference materials to reveal something like alpha spectroscopy of a single microparticle. Higher is alpha energy of a particle, longer is the track. So smaller is the final diameter under the same etching conditions. Alpha track radiography is a very useful instrument for characterization of alpha emitting nuclides, especially on the background of high beta activity. So to conclude about passive techniques, we can say that radiography is useful for contaminated samples because it could characterize the distribution of radioactivity in the sample evenly, unevenly, at macro and micro levels. And it is the best tool for searching some radioactively contaminated spots of local concentration. And it could help us to estimate the total radioactivity and alpha radioactivity separately in the same sample. That is about passive techniques. Let's go further to electron beam methods, which are based on electron beam induced methods. There are big family of electron microscopy techniques today. We will see briefly about the main two methods. The first is scanning electron microscopy, and the second is transmission electron microscopy. Both are based on the incident beam of electrons, but the acceleration voltage is different. For scanning electron microscopy, around 10-20 kilovolts is enough, because scanning electron microscopy studies only the surface of the sample. But transmission electron microscopy is to go through the sample, so the acceleration voltage is around 200 kilovolts. What kind of information and what kind of detectors used in these methods based on electron beam? The first methods is secondary electrons detectors, which could show the image in secondary electrons. The second is backscattered electrons detectors. There are several detectors close to the sample. The signal is much lower than of secondary electrons, and we will see the difference about this image in these images. The detector of characteristic X-rays, so it is X-ray fluorescence on the base of electron microscopy. And Auger electrons, on this base, there are special Auger spectroscopy microscopy. In the case of transmission electron microscopy, we can see inelastically scattered electrons, elastically scattered electrons, and we can see this kind of detectors show electron energy loss spectroscopy, and we can see diffraction to reveal the phase of your matrix or of your radionuclides form. So in this case, we can see imaging, spectroscopy, and diffraction. All three kinds of classes of methods, just in electron microscopy methods. Here it is the example of secondary electron image and backscattered electron image of the same place. You can see advantages of secondary electron image is that you can have higher spatial resolution. If you are to have morphology image, you use secondary electrons. But the advantage of backscattered electron image, it is not so good in spatial resolution, but it is good in composition contrast. You can see some heavy particle on the matrix of some environmental materials matrix, some light matrix. It is clear. So this uranium particle, here it is, we cannot separate it, we cannot see it in the mode of secondary electrons. And about morphology of different radioactively contaminated particles. Here it is the example of nuclear test site soil, which contain melted particles of this sand. It has the same composition, elemental composition as the sand. There are no heavy metals here in big quantity, but the surface is just different from other particles from accidental, for instance. So it is melted surface with some bubbles on it. In the case of Chernobyl soil, there are another morphology. It is just fuel particles with some grains of the original fuel and some channels of fission products which are to go from this matrix of dioxide of uranium and make such channels in this matrix. And this is another example of morphology of Chernobyl lava pumice fragments. Chernobyl lava is uranium zirconium containing silicate matter, which flow to the different floors of the former reactor. And here it is the example of bubble basin. It is the first floor of the reactor. It was filled with water, and when lava comes to water, it has some bubbles like pumice in the sea when volcano and lava goes to the seawater. But if you compare pumice from sea volcano, you can see that in Chernobyl lava there are some uranium dendrites, uranium O2 dendrites, and we can see some secondary minerals of uranium in these bubbles, which is the result of oxidation of uranium-4 to uranium-6 and forming of some uranyl crystals on the surface of this lava. It is another example of scanning electron microscopy analysis of contaminated site. It is the Enterprise, some soil around the Enterprise, and there are some remains of wood impregnated with contaminated solutions, uranium-containing solutions, and these solutions precipitates with uranium-6 phosphates, such crystals. And the backscattered electron mode is sensitive to atomic number and density of a sample, so we can see on the matrix of wood some black full background and white crystals of uranium phosphates. What kind of information we can obtain except images from scanning electron microscopy and transmission electron microscopy? The main advantage is the possibility to obtain elemental analysis. This is spectrum of some contaminated sample with plutonium. You can see it is EDX elemental mapping, where you can compare some uranium and zirconium and niobium from some hot particles from Chernobyl. And so it is elemental composition, and there is a possibility to obtain phase composition if you use diffraction mode. In scanning electron microscopy, it is electron backscattered diffraction in such way in lines of Kikuchi. And in transmission electron microscopy, you can see diffraction pattern, and you can calculate the crystal or amorphous phase. What is the parameters of this crystal grid? So electron microscopy analysis are very useful for our characterization of contaminated samples. This is the example of spectra. There are spectra of pyrite crystal and uranium oxide microparticles. There are images of them, and there are some examples from the same place. It is bottom sediments of a reservoir of liquid nuclear wastes on some Enterprise territory. There are some iron containing particles and uranium containing particles in different forms. So you can see here it is uranium with organics matter, and here it is uranium oxide and uranium with some iron and stainless steel fragments. And another methods is based on laser light. For instance, It is micro-Raman scattering spectroscopy. It is a method which could help us. It is a fingerprint method. So you are to have some library of Raman spectra. But in some cases, it is better than X-ray diffraction. For instance, for uranium oxides, we cannot separate different uranium or 2 plus X oxides using only XRD, but using Raman spectroscopy, it is very simple to see very thin different in these oxides. The physical principle is that laser source goes to the crystal, and it is a big signal of relay signal, and it is stopped by special diffraction grids. And we are interested in very weak scattering. Raman scattering is much weaker than X-ray diffraction, for instance. So this is vibrational modes of rotational vibrational modes, which we can see like a spectra. And advantages of Raman spectroscopy is that we can work through some transparent environment. For instance, we can put your sample into the glass vial and go to the Raman spectroscopy and see through this glass your sample and measure and study the phase composition of your sample. The next advantage is that it can work in hot cell, and we can see this method in Marcoule in France. They use it for spent nuclear fuel characterization just in hot cell. They have microscope, optical microscope there, and the Raman spectroscopy is outside, and laser goes by optical wire inside this hot cell, and the signal goes to the Raman spectroscopy. And after separating of some part of spent nuclear fuel, they can see what is the oxidation state of uranium in this fragment, and what will they do with this material. This is the example of complex using of scanning electron microscopy and Raman microscopy to analyze 3 particles, hot particles from Chernobyl origin. You can see that there are very different morphology. This is just uranium-2, like the original fuel matrix. This is the melted zirconium uranium oxide. According to Raman, it is zirconium tetragonal phase. There are some different polymorphs of zirconium oxide. The most stable in the environment is bedyllite monoclinic zirconia. Here it's Raman. You can see the difference. And here it is the particle of zirconia with very small amount of uranium on the edges of this particle. You can see that we can obtain the information from these different methods about elemental composition, about morphology, about phase composition with very good micrometers resolution. And you have some lecture about X-ray methods, as I understand, but I will repeat some words. Analytical X-ray methods could be realized today on the laboratory and could be based on synchrotron light. It is X-ray fluorescence methods X-ray tomography, X-ray diffraction, small angle X-ray spectroscopy, X-ray absorption spectroscopy in the modes of near range and extended fine structure. And we can obtain different kind of information: diffraction scattering, imaging in the plane and in the volume spectroscopy. And I would like to say that some time ago we said that we can perform X-ray absorption spectroscopy only in a synchrotron, but now it could be done just in our division. We have spectroscopy for X-ray absorption, XANAS. Some words about the physical principles. Maybe you know about it. So there are X-ray absorption is very good method because it is element selective. We have some matrix with different kinds of elements. If you go to X-ray diffraction method or micro-Raman, you've got a lot of different lines and peaks of different elements. But in this case, we can use the energy, the edge energy of absorption of the selected element. So it is element sensitive method. It is the great advantage of it. What is the spectrum of absorption? It has three main regions. Pre-age, age, it is the region of XANAS. XANAS is near-age structure spectroscopy. And then it is extended X-ray absorption fine structure after age. So this is two main methods which are used to obtain valence state of the elements of interest, and some local structure, local surroundings of this element in the crystal. And you can analyze any phase, any phase of a sample, solid phase, liquid, and gas, if you have enough atoms for analysis and enough light for analysis, if you have some useful signal. There is the example of XANAS information. You can see different kind of particles, which it is micro XANAS from different enterprises and Chernobyl particles. And what kind of information you can obtain from X-ray absorption near-age structure analysis? We can see valence state of definite elements, symmetry, existence of not full electron shells, and it is fingerprint method. If you can some reference materials, you can see the valence state of your sample for such elements as plutonium, uranium, and some else. It is very important to understand valence state because there are methods of different oxidation states in the environment. Another example is our work with uranyl and uranate samples from this is uranyl on different clays, organic matter, and this is shopite. It is oxide, hydroxide of uranium 6. All of this spectra is EXAF spectra of uranium 6. And uranate, it is not uranyl, carbonate of uranyl and phosphate of uranyl. So we can see type of the neighbors atoms. It is not just like a spectrum, EDX spectrum, when you can see just the name of the neighbor atom, but you have some information that plus minus 3, so you can oxygen distinguish from как будет сера? Sulfur, but not from азот, как будет? Nitrogen. And you can obtain coordination number with big error and interatomic distances with very good, in very good, like you can see the difference is around 0.02 angstroms in interatomic distances. And in these exact results, you can see geometry, some geometry characteristics of your structure of this element in the space of different. It could be complexes on the surface. It could be the minerals and some different kind of uranyl phosphates or carbonates. And let's compare X-ray fluorescence based on laboratory X-ray tube and on synchrotron X-ray. It is the different. You can see if you see the scale bar is equal to 1 millimeter. It is uranium, sulfur, and silicate and iron mapping of some fragment from contaminated, radioactively contaminated soil. And you have a spectrum, elemental spectrum, elemental mapping, and this is the optical image of this fragment. And if you use synchrotron light, the spatial resolution is much better. If you are to have such good resolution, you are to go to synchrotron with good micro resolution. It must have a special micro station. Not any synchrotron has such beamline, unfortunately. So the scale bar here is equal to 5 micrometers. It is uranium oxide particle. It is here. It is according to, if you use micro X-ray fluorescence, then you can use micro xanthus, micro exhaust just for this particle. It is very useful in synchrotron equipment. And we can say, according to scanning electron microscopy, that it has such morphology, this particle. It has only uranium without any other elements, according to mapping. And according to microexaufs, it is scopied. According to microxanthus, it is uranium-6 particle. So such different information from different local microanalysis. This is tomography, X-ray tomography. X-ray tomography. Не работает? Ага. Okay. We'll try to rotate it. This is the sample of Chernobyl lava, and it has very heterogeneous composition. It is silicate glassy matrix in which we can find different kind of crystals like high uranium zircon, chernobylite, and zirconia, and uranium oxide dendrites, and some stainless steel bubbles. And you can see the distribution of density using tomography. It is not elemental composition, it is only distribution of density. But it is very interesting to see what is it inside some sample. Slightly destructive methods. Have you any time? Yeah? No? Uh-huh. Slightly destructive methods, I mean particle-induced or proton-induced X-ray emission method. It could be used for analyzing of elemental composition. And on this base, we can use Rutherford backscattering and nuclear reactions for isotopic analysis when we see gamma rays or some particles after this excitation by protons or particles. And destructive methods is mass spectroscopy analysis. We use it to define the source of contamination. The fact is that plutonium isotope ratio depends on the reactor. There are different reactors with different kind of plutonium isotopes. Weapon-grade plutonium has another kind of ratio, and if you compare plutonium 241 to plutonium 39 and plutonium 240 to plutonium 239, you can separate different power of explosions during nuclear testing. It is high power explosions, it is Bikini Atoll, and this is the explosions of global fallout before 1962, and this one is low power explosions in Semipalatinsk test site. And if you compare these explosions with Chernobyl, plutonium ratios, you can see that here it is nuclear testing, and here it is Chernobyl, and plutonium ratio is very broad because it works for many for a long time, and the many plutonium isotopes have been formed during this work. So to conclude, we can say that the most informative non-destructive techniques for legacy waste characterizations are autoradiography, which is used for distribution of radionuclides and searching of local concentrations of them. There is a big group of electron microscopy methods for morphology analysis, main elemental composition analysis, and big group of X-ray techniques for structure analysis, local surrounding of atoms, a valence state of radionuclides, 3D tomography, and some else, and 3D and X-ray diffraction analysis with very good resolution. And micro-Raman scattering could help us in some cases for phase definition if you have a library of reference materials for it, because it is fingerprint analysis. And after that, we use destructive methods, including ICP-MS, sequential extraction, to see the partitioning of radionuclides among different fractions of mobility, and so on. Thank you for your attention.
Any questions? No? No. Okay. Thank you. So actually, today we will have one another lecture, but yeah, it should be at 5. So we have some time. We can start to make the final testing right now, and then it will be another lecture, so that we will not waste time. Okay.
Раз, раз, раз. Все, есть.
So let's move to our final lecture for today. It was not initially scheduled, but we believe that it is a very important topic about the digital technologies for nuclear facilities characterization. So, Andrei, please.
Good afternoon, dear colleagues. My name is Andrei Bundin. I'm a research executive at Neoland Group of Company. Briefly about us, Neoland is an IT and engineering company. We develop software to support different stages of industrial facilities life cycle, including nuclear facilities and, of course, including nuclear decommissioning. And today, I'm going to tell you and show you some practical experience of how modern digital tools could be applied for one of the most important decommissioning tasks, the characterization, both physical and radiological of nuclear facilities. As you know, decommissioning consists of several technological stages, including planning, characterization, decontamination, dismantling, and material management. Each stage has a set of procedures, most of which require collection and processing a huge amount of engineering data. For the purpose of characterization only, we need to obtain actual engineering configuration of the facility, perform material inventory, measure and calculate radiation situations and characteristics, estimate the radioactive waste amounts, and categorize them prior to the dismantling. None of these processes could be performed well with high quality and safety without using appropriate digital tools. Here you can see the general stack of applied digital technologies that we use in our practice to perform characterization. The core of all technologies is the so-called building information modeling technology. BIM model is a multi-purpose digital environment that contains structured engineering data and enables development and application of different additional specialized tools for characterization process, radiation calculations, and general analytics. Another important technologies are automation data capture tools that use for high performance, high accuracy physical and radiological characterization. So BIM model is a digital representation of 3D configuration of a facility systems, structures, and components combined with structured attributive data and other important information, and of course, connected documentation. The average BIM model of a nuclear facility, such as nuclear power plant, consists of more than 300,000 elements and more than 5 million attributes. All these elements and attributes are essential for decommissioning purposes. Just imagine how is it possible to manage all these data without the appropriate digital tool. Here you can see an example of how BIM model could be used for navigation and searching the necessary element or equipment, checking its physical characteristics, viewing its 3D model, role and place in the corresponding engineering system, including 2D layouts representation. It also works in the opposite direction when you find the element of interest on 2D layout scheme and then can easily switch to its attributes and 3D model. Then you can check the corresponding set of equipment and view the attributes and 3D representation. If necessary, you can also find attached archive design documentation. And again, you can move from a set of equipment to the whole parent's engineering system. Another feature is that you can check certain compartments, rooms, and spaces which were characterized. For example, choosing the room, you can check its photo panoramas, which are usually synchronized with 3D model. Later in the video, you can see the example of photo panoramas, and it's the process with synchronization with the 3D model. Exactly this. So having photo panoramas is usually to help the specialist to evaluate the actual situation and field. So usually BIM model is developed during the physical characterization of a facility. Performing radiological characterization requires another set of technologies combined with certain procedures, starting from preparation and initial analysis to radiological survey, estimations, and simulation. Here, I will show you these processes step by step. Preparation and initial situation analysis. It's quite obvious that the final goal of radiation measurement is to obtain data for subsequent calculations, which in our case are carried with a BIM integrated radiation calculation digital tool. Here, the most essential point is to define the number and position for measurement points. Due to this, we use simplification of BIM elements, which are equipments, tubes, cables, construction tanks, vessels, and so forth, by their representation as a simple geometrical objects, cubes, cylinders, spheres, or like flat barriers, which we call phantoms. Or if we have complex geometry objects, we apply the group of phantoms. Then a characterization specialist makes hypotheses about the radiation sources location in a given BIM model area. Thus, for initial analysis, we have 3D phantom model with phantoms defined as a radiation source and another group of phantoms defined as a barriers. So the measurement points are set in BIM model. The location of measurement points depends on the type for measurements, dose rates, alpha, beta counting, or just swipe sampling. The point's location is secured by coordinate system inside the BIM model and also linked to surrounding phantoms for better in-field positioning of measuring equipment. Then, after setting the measurement points, the characterization tasks should be planned. The certain tasks depend on the mission and typically include dose rate measurements, alpha and beta counting, gamma spectrometry, and swipe sampling. The task is usually given to the certain team of specialists. And here, at that point, we must be aware that specialists will perform the measurement exactly according to a given task and characterization plan in general. So for this, we use mobile devices such as industrial tablets with preloaded 3D model of a target area, measurement points and their location, and of course the measurement task for the given area. Using mobile devices, the specialist can do not only measurements, but also make photos of the system, structures, and components, which condition is important for further decontamination planning, such as metal corrosion or equipment destructions. After measurements are performed, all the collected data transfers from the mobile devices to the BIM model. Here on the video, you can see an example of a BIM model of a certain area fulfilled with the measurement points. You can choose any of the model points and check the corresponding measurement result. Then, using analytical tools, you can generate the radiation survey report using preset templates. This example of this process is just on this video. Okay, after all the measurement results are integrated in the BIM model, we can use the radiation calculation tools. There are two general calculation tasks, inverse and direct one. Solving inverse task, you can find the specific activity of a phantoms and consequently beam element by using phantom characteristics, geometry, material composition, and also the results of the dose range measurements in all measurement points in the given area. Having the specific activity of all beam elements, we can calculate the amount of rad waste and divide the radioactive waste by categories. Here is an example of such calculations, raw inventory report generation. So you can see the 3D model, the elements, its specific activity, and then how it's divided into categories and generated and uploads the information in the report. So it looks good, yeah? But there is more. After we know specific activities of all systems, structures, and companies, we can calculate the direct task, which is to find the dose rate volume distribution using the meaning of specific activities of the elements and their 3D configuration in the given area. So it's so-called direct task. You can see in the video the volume distribution of the dose rates using different cross sections like horizontal and vertical. These calculations are very important from radiation safety planning and management point of view. In this video, in this example, you can see an area with calculated dose rate distribution. Then we can see how dose rate distribution changed along with dismantling process. The algorithm provides decommissioning engineers with a necessary tool for radiation safety management and simulations. After all the characterization procedures are completed, all the necessary data collected in the MEB model, and all the radiation calculations done, the analytical tool enables automatic generation of joint physical and characterization report in a given template. The example of that process you can see in this video. So in practice, the report generation takes just like several minutes. So it would save a lot of time for the specialists. Okay. Well, now we move to the next set of technologies applied for automation data capture. As I have expressed before, the accuracy of the management point's position is essential for proper radiation calculations and therefore raw estimation and radiation safety assessment. But there are more critical factors we should take into account. Some of the facilities areas have strong radiation contamination and thus have limitation for human operations. And these issues could be solved by using unmanned technologies like drones or robotic platforms. Here in our company, we carry on several research and development programs and projects on both of the ways. The video shows the concept idea of the group of drones application for physical and radiological survey. Each small drone equipped with a sensor, which could be a portative laser scanner, dose rate measurement tool, alpha beta counter, and etc. Each drone has a flight route developed to cover the most possible area. Drones equipped with laser scanners fly and scan the target area to obtain the point clouds, which then are used for building beam model using artificial intelligence algorithms and tools for point cloud recognition. So there is example of obtaining the point clouds during their flight of the drones. Then these point clouds are processed with AI algorithm to obtain the beam model. So all point clouds are collected in the software. Okay, and then the drones usually have has limits in the battery charge. So when one drone loses battery charge, it goes to the base station, and another drone, which is fully charged, flies up and continue the survey from the point of the last drone. And thus we can obtain the constant information flow from the survey. Mostly all the collected data in real-time mode transferred to the base station and then directly to the beam model. All drones are equipped with in-house laser navigation system that powered by base station independently from GPS or other satellite navigation systems. Okay. The second technology that we applied for automatic data capture is a smart robotic platform. I will show you some videos that we obtained almost a week ago. We have a test series for robotic platforms, and these videos are presented in another presentation. Turn it on. Okay, this is the robotic platform. Is a dog-shaped 4-legs robot from Deep Robotics company. The robot's equipped with laser scanner, panoramic camera, and dose rate measurement tool. Here in the video, we tested the ability of the robot to move through complex facility environments such as stairs. And the test shows that this robotic platform performed it in a very good way. During the test, the robot proved the declared abilities. And here, in the test mode, the robot was remotely controlled. But in general, robots can work in the autonomous mode, navigating through the computer vision systems or using preload beam model as a map. Here on the video is the result of the laser scanning performed by robotic platform. Okay. Using our beam software, we can view and navigate inside the integrated point cloud of scanned areas. Now, in several seconds, you will see like the result of the scans inside the target area. As you can see, the accuracy and resolution of scanning is high enough to distinguish separate wires, dismantled elements, and debris. As far as it was a test mode, you can also see the shapes of robotic platforms and engineers and people around. So this point cloud model is built from the point clouds obtained in different rooms of the facility. So you can easily move like downstairs and see the next room, what is there. Okay, in parallel to laser scanning, the panoramic capture also were performed. Again, I would like to express that panoramic views are important for decommissioning specialists and engineers. It allows to see the real situation in the field without going there, which has the great value from radiation safety point of view. And also in cases when the specialist or involved contractor is located distantly. After all the point clouds are collected, we use specific algorithms to build the beam model of a facility. So here is an example of the beam model, and later the physical attributes are added to the model. So you can choose any element of the model, and in the right field you can see its attributes, physical characteristics, and all their correspondent information that you need to use. Okay. Here is the beam model, which were extended by the radiation measurements results and radiation calculations results. This is a 2D layer that shows the points of dose rate measurements. And then after dose rate measurements, we proceed radiation calculations, solving both inverse and direct tasks. And here in the model, you will see their cross sections in horizontal and vertical way of their dose rate volume distribution results. The green are the points of measurements. The green spots are the points of measurements. And then after the processing of all the information, we obtain the volume. The video is not so fast as I expected. Okay, here you can see the volume distribution of the dose rates. Depending on the purpose you need, you can apply different colors to the dose rate distribution. So green are the normally like the dose rates that are safety for work. Yellow are kind of dangerous, and the red one are extremely dangerous. This is a horizontal cross section of the dose rate distribution, and then we can apply it also vertical. Yeah, horizontal are on different layers. Yeah, and here we can use both horizontal and vertical dose rate distribution to see the whole volume picture of the radiation situation in a certain facility. Here is a combined model, joint model of the building information model and radiation model of the facility. So here you can use all the layers of the facility, like spherical panoramas, point clouds. You can switch from one point to another point to see the photopanoramas, which is synchronized to the beam model. So then you can, in the beam model, you can choose any of the elements you need and to check its attributions. You can generate different reports for any rooms, compartments. You can switch between the report and 2D documentation to again go back to the 3D to find another points of interest or target areas, depending on the task you need to do. So this is a quite multi-optional tool for using in different kind of decommissioning purposes. Like you can see the measuring points, check their measurement, radiation measurements results. You can even see the history of the radiation measurements if their dismantling procedures are going through the time. So you can do radiation measurements like once in a month and then check all the history back. And yeah. So it was like briefly introductions of the set of technologies that we've used for radiation characterization. Of course, these technologies are applied for a way more purposes like decommissioning planning, decommissioning solutions simulations, VR personnel training, and a lot of different areas. So if now you have any question according to the technologies or different parts of the technologies, you are welcome to ask.
Thank you. Any questions? I actually have one questions. You showed this. One question, and then you showed this result of the scanning of the space inside the building. But if there are some pipelines inside the walls, is it possible to add them to this?
Absolutely, because we don't only use the laser scanner result, we also use the design documentation. If there is a hidden amount of like pipes of wires, we also add it to the beam model.
Okay.
Thank you very much. Thank you very much for the presentation. And I just wanted to find out actually about the estimation that you talked about. So how accurate are these estimations? Are they reliable in this case?
Estimation of radioactive waste or estimation of the dose rates?
No,
distribution?
both.
Both?
Okay, the dose rate in this
Okay.
case, yes. How accurate are these
Okay.
calculations?
Usually we have a very high accuracy of estimation because we can also check their the algorithms consist of the system of equation to solve. The more points of measurement we have, the more accurate the result is. And we can also check the result by comparison their calculated result in a given point and the real measured exact in the given point. And that's how we estimate if the model is correct, what is the accuracy, and if it's satisfied us in this certain case.
Thank you very much. And also one more question. I wanted to find out about, you talked about the drone, where you use the drone to actually assess the area, so to say. And I actually wanted to find out, like, can't it be much more effective if we can actually install these sensors in a facility, like in the process of construction? Can't it be more safe such that if we want to maybe assess the dose rate in this case, we just turn on the sensor, maybe from afar, then we'll be able to collect data from, like, maybe I would say, okay, for example, let's say, I'll use an example in maybe Bangladesh. Like I know they are, I'm sure, almost done with the construction of the nuclear power plant.
Mm-hmm.
Can't it be much effective if we can install the sensors other than using drones? Because when we talk of drones, of course, we'll talk about the issue of exposure in this case. We'll need like maybe someone to actually disinfect. In this case, I'll use the word disinfect, because we also need these drones. In this case, they'll actually be, for example, in a nuclear facility, of which they'll also be exposed. And in that case, I was actually wondering, can't it be much effective? We can use maybe installed sensors within the facility. Yes.
Okay, yes, it's more fair for the new nuclear facilities, and new nuclear facilities, they have the wall radiation measurement systems with all the sensors and integrated system. But like 99% of the facilities that we face decommissioning, it's a legacy facilities. They were built like 50 more years ago, and they have like zero equipment for like radiation assessment or something. And most of the facilities, even, they don't have any design documentation. So we're faced with the problem like from the very zero. We don't know anything about it, and that's what we do. We try to measure to obtain like initial information. Of course, the new products of the new nuclear plants, they all use the integrated radiation safety and monitor system. And of course, this data we will use later, like in 50 years, when we'll do the commission of this. But for all facilities, no. The only way is to proceed the radiological survey in real time.
Oh, thank you very much.
Yeah. Any more questions? If not, then let's thank the speaker again. Thank you very much.
Thank you for the thing.
And we finish for today, and see you tomorrow.
Только минут 10 занялось.